Hello students, let us continue our discussion on current electricity and today a few more problems. Uh, Starting from question number 24, which itself has three parts in it, and each part is which can make one individual separate question itself. So that big they are. And don't need to worry, in board exams, they are not going to ask this kind of combination of three questions into one question, okay, in one question. So don't need to bother. uh, I can say they can ask each part of the question as single question for 5 mark. Okay, so this question is huge. It can be asked if they ask. Okay, they don't ask this kind of questions to put together, but each part of them itself weighs close to 3 to 5 mark. Okay, right. Let me take individual parts of the question. 24th question, the first question. Then why did they put together? They have put this together because again they are all related to combination of resistors itself. Okay, no other concept. That is why they have put this put the entire all those three parts into the same question, 24th one. Right, first part A, sub question A from 24th question is as follows. Given n resistors, each of resistance R, how will you combine them to get maximum, minimum effective resistance? What is the ratio of the maximum to minimum resistance? So now what they have given us is n resistors which are equal. All of them has the resistance of R. Okay, so when this is the situation, okay, remember always whenever you have a set of resistors given, then when you connect them in series, connect all of them in series, you get to maximum possible resistance. You connect all of them individually in parallel, you get least possible resistance out of it. Okay, be clear with this. This is the basic of getting maximum and minimum resistance. Clear with that? So connect them in series, you'll get maximum resistance. Connect all of them in parallel, you'll get minimum resistance. So that is what this question is about. So when it comes to maximum resistance, okay, write a sentence. Okay, maximum resistance can be obtained by connecting given resistors in series. Okay, so how many resistors do we have? N resistors, and each resistor has the resistance of R. So all of them put together, Rs in series, is equal to NR, isn't it? So it's the direct expression, and this is the maximum resistance that we can get by combining N resistors, each of resistance R. Okay, quite simple, series resistor, series combination. And now similarly, when it comes to minimum resistance out of the combination, write a sentence again. Minimum resistance can be obtained by connecting given resistors in parallel. Okay, so you have n resistors again, each of resistance R. That's it. Rp is equal to R by N. Okay, again direct formula, which itself is the solution. So these two are the answers for this and this question. But there is one more question inside this, which is what is the ratio of the maximum to the minimum? What is the maximum? Series one. Okay. What is the minimum? Parallel one. So they're asking us to get the ratio of maximum, which is Rs in series, to the minimum, which is parallel Rp. Okay, so it's the ratio of series combination, effective resistance of series combination to effective resistance of parallel combination. Maximum, minimum is equal to, what is Rs? Rs is NR. What is Rp? Rp is R by N. R and R cancels, which is equal to N squared. That's it. Okay. So the ratio of maximum to minimum resistance of the combination is N squared. Okay. So this is about the sub question A of 24th question. Clear? And one more important thing here, that even if you are not given with equal resistors, say you have resistors 1 ohm, 2 ohm, 3 ohm given, in this kind of situation, even in this kind of situation, if you connect all of them in series, those three put together will give you maximum resistance. You connect all of them in parallel, 1 parallel with 2 parallel with 3, that combination will give you least possible resistance out of the combination. Okay, so this law is valid even when you do not have equal resistors given. Clear with that? Okay. Okay, the next question, next part of the 24th question is as follows. Part B. Given the resistors of 1 ohm, 2 ohm and 3 ohm, 3 resistors, how will you combine them to get an equivalent resistance of 11 by 3 ohm, 11 by 5 ohm, 6 ohm, 6 by 11 ohm? So generally in board exams, these kind of questions are not asked. Okay, even if they ask you, the strategy will be to get the all possible combinations of these three resistors given. Okay, we have three resistors, 1 ohm, 2 ohm and 3 ohm. First we need to roughly draw, okay, all the possibilities of combinations, different possibilities of combinations. Okay, the first possibility is 1, 2 and 3 ohm connected in series. Okay, the second possibility, 1 ohm in its place but 2 and 3 in parallel. Okay, and in third you can write 1. Okay, let me go step by step. Let me take 2 here, 2 here and 1 and 3 here. Okay, now the other possibility is 3 ohm here in parallel combination of 1 and 2. Okay, yeah, they are different, all of them are different. 1 2 3 here, 2 3 1 3 and 1 2 here. So these are 4 combinations, we still have 4 more. Okay, look for that. You take we can have 1 and 2 in series with 3 ohm, right? This is also possible. And then replace them, just replace them. This is the basic structure. Okay, this one and this one, then all of them in parallel, 4 basic structures, and just playing with the values. So it's 1 and 3 here, okay, with 2 ohm here, right? And at last we can have 2 and 3 here, right? 2 and 3 here with 1 ohm here. Okay, see, even if you change 2 here and 3 here, okay, that doesn't matter, that won't change the values because it's simply series combination. Put 2 here, 1 here, the effective is still 1 plus 2, that's it. Okay, nothing to worry. And the last combination is parallel of all of them. Okay, it's 1 2 3, all of them in parallel. So these are the 8 possible combinations of given 1 ohm, 2 ohm and 3 ohm resistors like this. Now see, I drew all of them because we have 4 different values of resistances given as effective. Okay, if it was simply 6 ohm, I could have easily judged, right? Okay, obviously it is 1 plus 2 plus 3 which will lead me to 6, so it's definitely a series combination. But we also have different values like 11 by 3, 11 by 5, 6 by 11 and all. So when we want to look for all those values, we can't go with random combination. Okay, Yeah, you can go with random combination, but that they might not lead you to the final value of this. So the best approach would be to consider or draw all possible combinations and get the values randomly first, and then simplify them in a proper way. Okay, right. First, you look for this 1 plus 2 plus 3, all three in series. 1 plus 2 plus 3 is 6. So 6, yes, we have third one. Okay, this is random verification. Then after choosing the 4 combination, we will work properly. Okay, right. Next, let me come for this. You have 1 plus these two in parallel, right? So it's 2 3s are 6 by 5, right? 2 and 3 in parallel, 2 3s are 6 by 5. So it is 5. Over there it is 5 1s are 5 plus 6, 11. 11 by 5. Do we have 11 by 5? Yes, we have. So this is second one. Okay, and this is third. Next, you have 2 plus in series of this, which is see, R1 R2 by R1 plus R2, right? Remember that 3 into 1 by 3 plus 1. Okay, 3 into 1 by 3 plus 1. Take the LCM. 4 to the 8 plus 1, 11. 11 by 4. Do we have the value 11 by 4? So no, this circuit we don't need. Okay, because we don't have the value. Right, let us neglect it. Let me come here. So here I have 3 plus 1 and 2 in parallel. So it's 1 to the 2 by 1 plus 3, 3. Now the LCM is 3. 3 3 is a 9 plus 2, 11. 11 by 3. Do we have 11 by 3? Yes, we do. So this is the first one. Okay, so only one left now. Okay, let me come for this. So 1 and 2 in series, which will give me 3, right? 3 and 3 in parallel will give me 3 by 2. Do we have the value 3 by 2 here? No. So this is not a required circuit. Let me come here. 3 and 1 in series. So the effective is 4. 4 and 2 in parallel. So it's 4 2s are 8 divided by 4 plus 2. Okay, it's 8 by 6. Do we have 8 by 6 or 4 by 3? No, we don't. So this will also not help us. Now here 2 3 is a 2 and 3 in series. 5 is the effective, and 5 and 1 in parallel. So it's 5 ones are 5 by 5 plus 1, 6. 5 by 6. Do we have 5 by 6? So no, this is not so useful for us. Let me come here. 1, 2 and 3 in parallel. Okay. So yeah, you can make use of 1 by RP. Okay. So 1 by RP is equal to 1 by 1, 1 plus 1 by 2 plus 1 by 3. LCM is 6. So it's 1 6 2 3 plus 3 2 So it's 11 by 6. What is that? 1 by RP. So RP is 6 by 11. Do we have that? Yes, we do have. So fourth one is this. Clear? This is how randomly you should verify. Okay. You might ask, sir, will we be having so much of time? Yes, you will be having plenty of time, because you need to write only for 70 mark, not for 100. Okay. You'll be having 3 hours. So you'll have plenty of time for solving problems. But again, you need to be quicker. Okay, and this is the approach. Stick with this approach and solve. Okay, now I'll remove all the unnecessary circuits. So after removing the unnecessary circuits, we are left with only the required one. And now we'll go in order. The first one, where is the first one? Here is the first one, which gave us 11 by 3. Okay, so the possible combination for first one is 3 ohm in series with the parallel combination of 1 ohm and 2 ohm. Okay, so now you see, this is just random verification, but when it comes to the actual solution, you should do it in detail. Okay, you name them as this as R1, this as R2, this as R3. Okay, so R1 and R2 in parallel, so you call RP is equal to R1 R2 by R1 plus R2. What is that? 1 into 2 by 1 plus 2, which is 2 by 3. Okay, then you put RS is equal to R3 plus RP, right? RP is this combination. So R3 is 3 ohm, RP is 2 by 3, which is equal to Uh, yeah, 3 is the LCM, 3 3 is 9 plus 2, 11. 11 by 3 ohm. So, and hence verified for the first one. Here, this is the actual procedure which you should do completely. So, in the same way, you have to do for the rest of them. Here are the circuits that I have already given. Okay. And you should follow this pattern. You name them as R1, R2, R3, and then simplify to get RP, and then uh, RS together. Okay, you have solved. We have discussed so many problems like this. So you have to do the same kind of solution for the rest of the circuits, the three of them. Okay, this is simple. All of them in series. Again, this is also simple. All of them in parallel. For this, work with these two first. Name them as R1, R2, R3, or R1, R2, R3. R2, R3 in parallel. Solve for Rp is equal to R2, R3 by R2 plus R3. Okay, you have to put the formula. Okay, formula carries mark. So that is how, with the same approach, you simplify the rest of the circuits and put the values. Clear? Okay, last part of the question, part C of 24th question. Determine the equivalent resistance of the networks shown in figure A and B. Okay, so in fact you have two networks given. I have only taken the first network given in figure A. Okay, so in the question itself they are going to give you the network. So the network is as follows. Okay, here you have 1 ohm, 1 ohm, 1 ohm, 1 ohm, 1 ohm, 1 ohm resistors. Here you have 2 ohm, all of them 2 ohm resistors. Okay, so now again the approach would be to look for the simplest combination in the network. See, you can observe between these two you have 1 ohm and 1 ohm in series, right? And from this point it splits. It has become a bit complicated. So we are not going to bother about what is happening after this point. Instead, we'll look what is happening between these two. Yeah, it's quite simple. We have two resistors in series. That's it. Similarly, you come here, two resistors in series. Similarly, here, two resistors in series. Here, two resistors in series. And you come here where you have again two resistors of 2 ohm in series. Series. So, one approach would be by reducing, we'll keep on reducing the circuit. But before we reduce the circuit, you simply put the formula of R1s. Okay, it's always suggested to keep the formula. So RS1 is equal to R1 plus R2. Okay, R1 is 1 ohm, R2 is 1 ohm itself. So 1 plus 1 is equal to 2 ohm. Okay, you have two equal resistors. Even if you can put 2R. Okay, that's also fine. Similarly, RS2, okay, we are talking about this part of the circuit, is equal to, you can call it as R3 and R4 or 2R2. That's also fine. R3 plus R4 is equal to 2 plus 2 is equal to 4 ohm. Okay. Instead of R1 plus R2, you can also directly write 2R1 here. Instead of R3 plus R4, you can again directly write 2R2 here. Okay, that's also fine. This is also fine, this method. But either that or this, you have to write that in once like this. Okay, then we will reduce the circuit. Okay, after writing this, we will reduce the circuit. Now the circuit looks somewhat like this. Point A, from here, see, instead of 1 and 1 in series, I can directly write 2 ohm. And similarly, instead of 2 and 2 in series, I can directly write 4 ohm. Okay, and the point will join again at this point, and the same pattern continues. How many times? 1, 2, 3, 4. 4 times. Okay, so this is how the reduced circuit look like. Okay, 2 ohm, 4 ohm in parallel, one combination, with 2 ohm, 4 ohm again in parallel, another one, 2 ohm, 4 ohm in parallel, 2 ohm, 4 ohm in parallel. So this is the reduced circuit. Now let me work for the effective. Now again, this is a complex circuit which involves 8 resistors. Now out of all these resistors, which is the least possible, or the easiest combination? What is the easiest combination? See, this 2 ohm and 4 ohm in parallel is the easiest combination of the entire circuit. Okay, this part. Similarly, even this is also the similar way. So let me work for the effective of these two in parallel first. So let me name them as RP. RP is equal to, see, I have named this as RS1 and RS2, but I can also name this temporarily. Any name, name is fine, but don't repeat them. Okay, since I have already named them as R1 R2 and so on. Okay, let me keep this as RS1 and this as RS2. So RP is equal to RS1 RS2 divided by RS1 plus RS2. Got it? Is equal to, because RS1 and RS2 are in parallel. You can name them as R5 and R6. That's also fine. But since I took them as RS1 here, I just try to keep the name as RS1. That's it. Okay. Right. So what is RS1? 2. What is RS2? 4 ohm. So it's 2 into 4 by 2 plus 4. 8 by 6, which is equal to 4 by 3 ohm. So now this combination will give us 4 by 3 ohm. Okay. And hence, once again, the circuit can be reduced now to this form. Okay. The combination is giving me 4 by 3 ohm of resistance. So 4 by 3 ohm, 4 by 3 ohm, 4 by 3 ohm, another 4 by 3 ohm of resistance. A, B. Okay, clear? So 4 by 3, 4 by 3, 4 by 3, 4 by 3. Now all these 4 by 3s put together in series, since they are all equal and in series, I can write the effective combination RS is equal to, since I took this as RP, okay, this one combination as RP, so RP is 4 by 3. So RS is equal to how many resistors? 4 resistors. So 4 times RP. Okay, remember, when you have n equal resistances in series, the effective resistance is RS is equal to NR, isn't it? So similarly here, RS is equal to N is 4, resistance R is RP. Okay, since I named this RP, I kept it. You can keep it R, that's also fine. So it's 4 into, what is RP? Each resistor is 4 by 3. So RS, the final effective resistance, is 16 by 3, which is equal to 5.33 ohm. Clear? So this will give us the effective resistance of this combination. Easy, right? Okay. Stick with the approach properly. We can get it. So this is the figure B, the second circuit given for the same 24C question. Okay, the circuit seems to be very simple, but again, this is to check your understanding of series and parallel combination, because whenever we see resistors put like this, we suddenly assume that okay, it is parallel. No, it is not. You should observe carefully. They are not connected end to end. They are connected in series like this, isn't it? See, here is the point where the circuit starts, and nowhere the circuit splits. It's continuous and all the resistors are in series here, right? So it's not somewhat like parallel, it is actually a series combination. Okay, I can stretch it. If I stretch it like this, all the 5 resistors will come here. Okay, isn't it? So it's the series combination and all the resistors given are equal. So it's quite simple. RS is equal to N times R is the formula. You write the formula once. Then RS is equal to N, how many resistors? 1, 2, 3, 4, 5. 5R ohm. That's it. Okay. This is the effective resistance of the given circuit. Okay, moving ahead for the next question, 25th. We have the question as follows. Three resistances are R plus 2 and 2 of R plus 2 are connected in parallel. Okay, their equivalent resistance is 2 ohm. Find R. Okay, 3 resistance whose values are not directly given, instead they are put with the R value, and we now need to, and the effective resistance is given when they are combined in parallel, and asked to find the value of R. Okay, right. Now, if the combination is connected to a battery of EMF 3 volt and negligible internal resistance, calculate the current in each of the resistance in parallel. Okay, again the question has two parts in it. The first part is finding R, then the second part is finding the current in each part of the circuit, each resistance. First, let me draw the circuit. How does it look like? Here in this question they are not giving you the circuit. Okay, we should draw the circuit. Now see, you have three resistors. Okay, R, the other is R plus 2, and finally it's 2 of R plus 2, all of them connected in parallel. Okay, and the effective combination, effective resistance of the combination, Rp, since all of them are in parallel, I can take Rp as the effective one. So Rp is given how much? 2 ohm, right? Equivalent resistance is 2 ohm, and they're asked to find the value of R. Okay, right. So for the parallel combination, you write our formula once: 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3, because we have three resistors. This can be considered as R1, and this as R2, this as R3. So 1 by Rp is 1 by 2 is equal to 1 by R1, which is 1 by R, plus 1 by R plus 2 plus 1 by 2 of R plus 2. Clear? Okay. Now let's take the LCM. So it's 1 by 2. See, it's more math from this step. Okay. It's the quadratic equation form it will take, and we should solve it. Okay. See, what is the LCM now? LCM is R 2R, in fact. Okay. R into 2 of R plus 2, right? So I can write 2R of R plus 2 is the LCM, right? Following? Now you have R here. What is not there? It is 2 of R plus 2, which is not there, plus R plus 2 here. What is not there? 2R is not there, plus 2 of R plus 2 is there. What is not there? Only R is not there. Okay, taking LCM, you should be aware of all these things, basic maths. Okay, so now I can cancel this 2 and 2, right? And bring this R of R plus 2 here. At the same time, I can simplify. Okay. Okay, let me simplify the next step itself. R of R plus 2 is equal to, what is left here? 2 of R plus 2 plus 2R plus R. Okay, right. Now let me simplify. R into R squared plus 2 into R, 2R is equal to, taking 2 inside, 2R plus 2 into 2, 4 plus 2R plus R. 2R and 2R cancels. Now, here is what you have, R squared. Look at this, R plus 2R is, okay, R square is left, that's it, is equal to R plus 2R, 3R plus 4. Bring them here. So you have a quadratic equation now, which is R squared minus 3R minus 4 is equal to 0. Okay, right. Let me look for the factors. Shall we get the factors? 4 minus 4. No, there are no factors which can be obtained directly for this. Minus 4, sure, can we get some? Yeah, we can get it. Minus 4, no, and minus 3 is what we need. So it's 4 times 1, and we need minus 3, so it's minus 4 and 1. These are the factors, right? Right. So simplifying this, it's R squared minus or plus R minus 4R minus 4 is equal to 0. Okay, minus 4R plus R minus 3. Okay, so I can take R as common factor. R of R plus 1 minus 4 of R plus 1 is equal to 0. Okay, now look, finally you have R plus 1 into R minus 4 is equal to 0. which means either r plus 1 should be 0 or r minus 4 should be 0. If r plus 1 becomes 0, r becomes minus 1, and resistance can never be negative. Okay, theoretically it can be 0, but it can never be negative. So r cannot be negative, so I'll just neglect this and take this factor. R minus 4 is equal to 0. When I have r minus 4 is equal to 0, r becomes 4 ohm. That's it. So we have successfully obtained the value of r as 4 ohm. Clear? Okay, let's go for the next part of the question. So the next part of the question, we found our next part of the question is asked, if the combination is connected to a battery of EMF 3 volt. So this combination is connected to a battery of EMF 3 volt and in negligible internal resistance, 0 ohm internal resistance. Calculate the current of the resistances in parallel. So now we need to calculate the current in each branch. Okay, let me name the current in this current through this branch be as I1, and this as I2, and this as I3. Now again, this is the basic about the battery. You have 3 volt EMF given and the internal resistance is 0 ohm. When we have negligible internal resistance, both EMF and voltage of the battery, which means EMF and TPD of the battery, will be same, isn't it? We know that, right? So voltage across all the 3 resistors, okay, is 3 volt. Voltage across all the 3 resistors and the entire combination, okay, because they are connected in parallel, right? So this kind of question we have already solved. So now what we need is current through each of them. We have voltage through each of them, okay, and we now need current through each of them. Okay, you can name them. Okay, if you name them, you can you might find it easy. Let me name A and B for the entire combination, then C, D for this part, and E, F for this part, and G, H for this part. Yeah, avoid using E because E represents EMF here. Let me put some K. Okay, so now look at this. What we need is current through each part of the resistor. Let me go for the first part of the resistor. R is 4 ohm. Okay, so between G and H, between G and H, applying Ohm's law, V is equal to IR, so I1 is equal to V by R1. If I name this resistance as R1 and this as R2 and this as R3, so I1 is equal to V by R1. What is V? V is 3 volt, common for all of them because they're all in parallel. What is R1? R1 is 4 ohm, right? So it is 3 by 4 ohm. Current, ampere. Okay, 3 volt voltage, 4 ohm resistor. That's it. Now, so you have I1. This is one of the result. Now between K and F, you have the resistance of R plus 2, right? What is R? 4 plus 2 is 6 ohm. So R2 is 6 ohm here, right? So I2 is equal to V by R2. V is 3 again, but R2 is 6 ohm. So it is half ampere. Okay, I2 is half. Similarly, between C and D, okay, between C and D, we have the current flowing I3, which is equal to V by R3. V is 3 volt. What is R3? R3 is 2 of R plus 2. What is R2? 2 plus 2 is 4. Oh, wait a minute. I'm sorry, not RP, R. Okay, R is 4 ohm. Okay, so it's 4 plus 2, 6. 6 2 is a 12 ohm. Right? 12 ohm is the resistance which shall be considered as R3. So it's 3 by 12. So 3 ones are 3 fours. It's 1 by 4 ampere or 0.25 ampere is the current through this branch of the circuit. So we can replace this 0.5 ampere, you can write, and this as 0.75 ampere. Okay, so and hence we have the current through each branch of the circuit, each resistor, in other words. Then what is the main current? Okay, main current is sum of all these three. You can also directly get it. 0.75 plus 0.25, 1 ampere. 1 plus 0.5, 1.5 ampere is the main current drawn from the battery. Okay, clear? Good. Right, the next question, 26, is as follows. Again, this question has got two parts. Let me read the question. Two cells A and B are connected in series. Now this is the question about cells, okay, not resistors. It's the cells. Two cells A and B are connected in series, each having an EMF of 1.5 volt, okay, and each having the EMF of 1.5 volt. The internal resistance of A and B are 0.5 ohm and 0.25 ohm respectively. So which means A has the EMF of 1.5 volt and internal resistance of 0.25 ohm. B has the EMF of 1.5 volt itself, but the internal resistance, A has the EMF internal resistance of 0.5 ohm, but B has the internal resistance of 0.25 ohm. Both has the EMF of 1.5 volt. Clear? Both has the EMF of 1.5 volt, but they have the different internal resistance. A of 0.5 ohm and B has 0.25 ohm. The combination is connected across a resistance of 2.25 ohm. So this is the external resistance connected for the combination, for the series combination given. Now calculate the current in the circuit, I, the potential difference across the terminals of each cell. Okay, let us go step by step. First, let me draw the circuit. So the circuit is quite simple and is as follows. We have two cells A and B connected in series, right? Let me call this as cell A and this as cell B connected in series. Okay, each has the EMF of 1.5 volt. This has the EMF of 1.5 volt, even this has the EMF of 1.5 volt. But the internal resistance of A is different when compared to the internal resistance of B. So A has the internal resistance of 0.5 ohm and B has the internal resistance of 0.25 ohm. So this is the combination, okay, and this combination is connected across a resistance, which means an external resistance of 2.25 ohm. Okay, now current in the circuit has to be calculated, right? Not like this, sorry. So it's current, the total current in the circuits, it's in the, all of them are in series, no? So the current will be same throughout the circuit. And not only current, potential difference across the terminals. So potential difference between these 2 points across the terminals of the cell, okay, which I can call VA. VA is the voltage across or potential difference across first cell, across the terminals of first cell, and let me call this as VB, which is the potential difference across the second cell. So voltage across first cell A and cell B has to be calculated. Okay, I, VA, VB, these are the terms which has to be calculated. Let me name this 1.5 volt EMF of the cells as E1 and E2. Okay, or I can also call them as EA and EB. That's also fine. Okay, let me call them as EA and EB itself. EA is 1.5 volt EMF of cell A. EB is 1.5 volt itself EMF of second cell or cell B. And let me call the resistance, internal resistance of cell A as RA, small r A, which is 0.5 ohm. And similarly, internal resistance of cell B shall be called as RB, which is 0.25 ohm. Now, when you have such a situation where you have two cells connected in series with an external resistance and you want the current, okay, we should always look for the effective EMF, uh, and effective internal resistance of the cell, okay, of the cell combination of the cells. So which means first we need to take the effective cell for the combination. Okay, effective cell will have the EMF of combination and resistance of combination. Okay, so effective, since they are in series, it's quite simple. ES is equal to E1 plus E2, right? I can also write EA plus EB, that's also fine. Okay, EA plus EB. What is EA? EMF of first cell, 1.5 volt. What is EB? 1.5 itself. So the effective EMF of the combination of these two cells put together, ES, is equal to 3 volt. Okay, so you have effective EMF. Then come to the internal resistance part. So since again the resistors are connected in series, internal resistance will be simply RS is equal to R1 plus R2. I can put them as RA plus RB. What is RA? RA is 0.5 plus what is RB? RB is 0.25, which is equal to 0.75 ohm. So these values gives us the characteristic of the effective cell. Okay, so now the circuit, just for the reference, will look somewhat like this. A single cell connected to an external resistor. This single cell has the EMF of 3 volt and internal resistance of 0.75 ohm, and the external resistance is 2.25 ohm. We normally represent external resistance as R, you know that, right? So current has to be found now. Quite simple. Current formula, I is equal to E by R plus R. Okay, I is equal to E by capital R plus small r. What is E? EMF of the effective cell, okay, of the combination, which is 3 volt divided by capital R is external resistance of the circuit, right? So this is the simplest circuit now. Now we are solving on that. External resistance is 2.25 ohm plus small r is internal resistance. Internal resistance is 0.75 ohm. So it's 3 by 3, which is equal to 1 ampere. So the main current flowing in the circuit is 1 ampere. Clear? Which means current through this point is 1 ampere, current through this point is 1 ampere, here 1 ampere, 1 ampere, 1 ampere, 1 ampere, 1 ampere. Everywhere in the circuit it is 1 ampere. Okay, so first part of the question is answered. And now in the second part of the question, we need TPD, terminal potential difference across cell A and across cell B. What we know is the current through cell A and current through cell B, which are equal to 1 ampere. So you have the current flowing through them. Yes, we have 1 ampere, right? And we also have the EMF of each of them, 1.5 volt, 1.5 volt. We also have the internal resistance, 0.5 ohm, 0.25 ohm. What we need is TPD, the relation between voltage or TPD, okay, and the EMF and current. Okay, you remember the formula? Simple one. It says V is equal to E minus IR, right? The very familiar formula of cell. So what we need is V. Okay, I can call that as VA, applied for the first cell, cell A. And instead of E, I can call it as EA. Current is same, so I'll just keep it EI. Instead of R, I'll write it as RA. Okay, so now VA is equal to, what is EA? EMF of the cell A is 1.5 volt minus, what is current through that? 1 ampere into, what is the internal resistance of cell A? 0.5. So it is 1.5 minus 0.5, which will be 1 volt. That's it. You have the value of voltage drop or terminal potential difference. Both are same. Terminal potential difference, voltage drop, potential drop, all of them are same. Across the first cell, across cell A is 1.5 volt. Is 1 volt VA. Okay. Similarly, you solve for VB. Okay, solving for VB in the same way, I can write VB is equal to EB, EMF of cell B, minus current through cell B, which is same as current through cell A and through the entire circuit, into RB, which is the internal resistance of cell B. So VB is equal to, what is EB? EB is 1.5 again, minus current is 1 ampere into RB, internal resistance of cell B, 0.25 ohm. So it's 1.5 minus 0.25. So VB, voltage across cell B, is 1.25 volt. Okay, that's it. We have answered all the questions. And if they ask you to get the voltage across the resistor, okay, when you want the voltage across the resistor or voltage across the entire combination, both are same, okay, then it is sum of VA plus VB. So it is 1 volt plus 1.25. 2.25 volt is the voltage across the entire combination. Okay, you can verify it. 1 plus 1.25, 2.25. Now, one more interesting fact, just for checking it out. See, voltage across the resistor is 2.25 volt. Resistance is 2.25 ohm. Current is 1 ampere. So you put the values into Ohm's law. V is equal to IR. V is equal to I into R. 1 into 2.25 is equal to 2.25 volt. So Ohm's law is still valid, right? Just for the verification, you can do that. Clear with the solution? This is how we'll solve this question. And one more thing. Yes. Yeah. Regarding the test. Okay. Yeah. Say the test that you are going to take on Monday will have will not have potentiometer from current electricity. Okay. I have given you the syllabus. In the syllabus, you have the the current electricity chapter, both problems and theory. Okay, but since I could not complete potentiometer, I just directly, since I came directly to problems of the current electricity chapter, potentiometer part will not be included for this test, and it will be included for the coming test. Okay, which will give later. So potentiometer will not there for this test. Okay, and this is there in the syllabus. Okay, it's there in the syllabus, but for this test it's not included. And when it comes to rest of them, all of them are there. Okay, you can find plenty of derivations from the chapter. Okay, there are plenty enough for 30 mark. Then when it comes to problems, the kind of questions that we have solved till now, we have solved somewhat like 26 problems, and out of this 26 problems, you will get few problems according to the pattern that I'll give now. But don't need to worry about the problems left out, because you have plenty of other problems left out, which are based on Kirchhoff's voltage law, Kirchhoff's current law, Wheatstone's network and all. I have not covered them. Okay, I'll cover them, but for the as of the test is concerned, you don't need to worry about the rest of the kind of the problems. So you just work on the problems which I have covered till now, till 26th question. Okay, and you can't expect the same questions to be repeated. Okay, obviously there will be difference in the value of values, and yeah, I can even change the pattern of the question, but the concept will be within the 26 questions pattern. Okay, right. So that is about exact syllabus for the coming test. Yeah, and the pattern of the question paper will be as follows. You will have 5 1-mark question, uh, so no option, 5 mark, and you'll have 3 2-mark questions, out of which you need to answer only 2, so 4 mark. Again, 3 3-mark questions, out of which you need to answer 2, so 6 mark. 3 5-mark questions, out of which you should attend 2, so 2 5 is 10, and you'll have 2 problems given. Out of them you should attend 1, so 1 mark, 5 mark from the problems. All of them put together, 10 plus 10 plus 10, 30 mark test. Okay, do it well. You can expect the questions to be similar, okay, not the same, similar to what you have in the given reference. Okay, because in the given reference they have put the questions in question and answer form itself. So you just go through them, that's enough for now. Okay, and read NCERT once if you get enough time for covering 1-mark questions.